So static means Mach number can be less than 1 or greater than 1. It can be subsonic or supersonic. And stagnation means Mach number is 0. And sonic, Mach number will be 1. Stagnation, Mach number will be 0. So the stagnation properties we are using 0, P naught, T naught, rho naught to denote it. And sonic we are using star. So P star, T star, rho star, etc. and all. So these are all the three cases. We are going to relate P1, P2 here, P and P naught here, P star and P naught. And the first one is very important. Maximum in the 12 mark they will ask this. Sometime they will ask other two cases also. So in this slide I explained just the procedure how to derive this isentropic relation. So it starts with the first law of thermodynamics. Then from that I am deriving change in entropy equation. You know the change in entropy value for isentropic flow. The process is reversible. So it is 0. Okay. So entropy is constant and change in entropy is 0 for isentropic flow. By making this as 0, I am going to relate temperature and this is specific volume. Okay. Normal volume is mass per density. This is specific volume, that is unit mass. So instead of this V2 by V1, I can substitute ρ1 by ρ2. So now I can relate temperature and density. I will get this final step. Then I have to relate pressure and temperature. So simply I can use this ideal gas law. Then using these two I can derive the last one. So these two equation only we are going to derive. This equation already you studied in thermodynamics, right? Is that clear procedure?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So first law of thermodynamics, then change in entropy, from that density temperature, then using ideal gas law, pressure and temperature we are going to relate. So now in the first slide, I am going to explain how to get this change in entropy equation from the first law of thermodynamics. So this is the first law of thermodynamics. It may be rearranged. dq is equal to dE plus dW. And dE I can write it as CV dt, dW just pressure work, PdV. So this V is the specific volume, okay. And dQ, I can take this change in entropy equation. So this is change in entropy. ds is equal to dq by t. So I can write dq is equal to tds. So I have now three terms that I can substitute in this first equation. So if you substitute, instead of dq it is tds, instead of de it is cv dt, and instead of dw it is pdv. Okay. So the first law of thermodynamics I converted like this from here to here. Now I need only the ds term. I don't want this t. So divide this equation by t. So t get cancelled. You'll get only ds. Here I am getting cv dt by t. Here I am getting p dv by t. So final equation is this one, s2 minus s1. That is in terms of s. So in that case I have to integrate this equation. So the first term if you integrate you will get s2 minus s1. This term dt by t if you integrate you will get ln t2 by t1. But this term I cannot integrate it. So if it is dv by v, then I can integrate it. So I have to change this term. So this p dv by t, I am going to change it so that it will be easy to integrate. So to change that, again I am using that ideal gas law, p is equal to RT. So if you rearrange, p by t is equal to R by v. So instead of this p by t, I am going to substitute R by v, so that you will get this equation. Same, ds is equal to cv dt by t plus R dv by v. Now I can integrate it. So you will get s2 minus s1. This one if you integrate and substitute the limits, you will get, so this is constant. Okay. So whatever we are discussing here is calorically perfect gas. So calorically perfect gas means temperature will be less than 1000 Kelvin, where Cp and Cv are constant. So this Cv is constant, gas constant also constant. So simply we are integrating dt by t. So it will be ln t2 by t1 plus r ln v2 by v1. So this is the first equation we got it. Is it clear?
Yes, sir.
Okay. Okay.
Yes, sir.
Yes, sir.
So, okay, thank you. So now first step is over. Now we can find density temperature pressure temperature relation. So just now we derived this term. You know, for isentropic, entropy is constant and change in entropy is 0. So this term we are making 0. So we have the remaining term. So this one I have to simplify so that from this I have to derive this final step. So the final step will contain only density, temperature and gamma. There is no CV or etc. and all. So every time I have to change it. So first I am rearranging it. So for example, take this CV ln T2 by T1 to the left hand side, otherwise R ln V2 by V1 to the right hand side, something you change it, you will get this term. And I don't want this CV by R. So I know CV equation. CV means specific heat at constant volume, which is equal to R divided by gamma minus 1. So CV by R, I can write it in terms of gamma, 1 divided by gamma minus 1. So substitute here instead of CV by R. Then I can take this to the power because I have natural ln I have. So I can take this to the power. So ln V2 by V1 is equal to ln T2 by T1 power minus 1 divided by gamma minus 1. Like that I am changing. See here it is not looking properly, so I written here. So first step I put 0, then rearrange, and I don't want this CV by R term. So instead I'm using this 1 divided by gamma minus 1 term. Then take this to the power so that you will get this term. Now you can cancel ln on both sides. So remaining you will get V2 by V1 is equal to T2 by T1 power minus 1 divided by gamma minus 1. Okay. Then I know specific volume means 1 divided by density. Then substitute, you will get rho 1 by rho 2 is equal to T2 by T1 power minus 1 divided by gamma minus 1. But in the gas table, everywhere they will use rho 2 by rho 1. So simply the inverse term. So simply if you take 1 divided by these two terms, you will get rho 2 by rho 1 is equal to this one. If you take it to the numerator, that minus sign will get cancelled. So it will be T2 by T1 power 1 divided by gamma minus 1. Is that clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So now this is the final term. Sorry. So rho 2 by rho 1 is equal to T2 by T1 power 1 divided by gamma minus 1. I think same derivation you studied in air breathing propulsion also, right?
Yes, sir.
Okay. Then okay.
Yes, sir.
Okay. So now we can relate pressure and temperature. So we are using the simple ideal gas law. P is equal to rho RT. So if you apply this to the control volume on both sides, station 1 and 2, you will get P2 by P1 is equal to rho 2 by rho 1, T2 by T1, R by R you will get it, that get cancelled. And just now we found instead of rho 2 by rho 1, it is T2 by T1 power 1 divided by gamma minus 1. So that time I am substituting. So here the power is 1 divided by gamma minus 1. Here the power is 1. Then we can rearrange T2 by T1 is equal to the whole power 1 divided by gamma minus 1 plus 1. And we can simplify this term. For example, 1 divided by gamma minus 1 plus 1. So if you cross multiply, you will get like this. So in the bottom it is same. You can take the common term. And above it will be 1 plus gamma minus 1. 1 get cancelled. Remaining gamma divided by gamma minus 1. So this is the second term. P2 by P1 is equal to T2 by T1 power gamma divided by gamma minus 1. That's it. Two terms we found it. So first term density temperature, second term pressure and temperature, and here they just combined all three. This is the relation between static P2 by P1 or ρ2 by ρ1. So now we can go for the static and stagnation. So before that, we will see where we can apply this. Maybe already you solved many problem in that air breathing propulsion. So for example, if you take aerodynamics, assume flow over the aerofoil, and these are all the free stream properties. So we know M1, V1, P1, ρ1, T1, etc. and all. And from the pressure port on the aerofoil, we found the P2 also. From that, we have to find density, temperature, Mach number, velocity, everything you have to find it. So in that case, you can apply this isentropic relation. So if you take this first equation, so we know P1, we know T1, and P2 also it is found. So from this relation, you can find the T2. Okay. So from this relation, so we can find the T2. Okay. So now we know ρ1, T1, T2. Now we have to find the ρ2. So ρ1 is given, T1 is given, T2 just now we found it. From this, you can find the ρ2. And once you know all this pressure, temperature, density, we can find the Mach number. How to find Mach number? Velocity or Mach number?
Under root gamma RT.
Under root gamma RT will give you speed of sound. I am asking local speed V2.
Oh, sorry. Yeah.
Sir, under root R into T, sir.
Sorry, ma, under root?
R into T, sir. Gamma will not be there.
No, gamma will be there. Yesterday only explained, right?
Mach is
Sir,
V by A.
no.
A is equal to root of gamma RT. This is
V by.
this is
M
for
is equals to V by A, sir.
Acha, oh yes, sir. M is equal to V by.
Yes, sir.
Okay.
Then it would be like we can find V2 from
how to find
this
V2?
equation. Sir, ρ2 by ρ1 equals to wait a second, sir.
To find Mach number V2 by A2, and to find A2, it will be gamma or T2. So T2 is known. Okay, gamma is constant, R also constant. So M2 you can find it once if you know the V2. How to find V2?
So V2 by V1 equals to T2 by T1 power minus 1 upon gamma minus.
This is
yeah.
This is
So
not,
this equation,
this is the,
left hand side bottom equations are in this slide. The top equation.
this is specific volume.
Oh.
So normal volume formula is mass divided by density. Specific volume means unit mass. That's it. This is not velocity. So simply you can use momentum equation P plus rho V square. Okay. So throughout this area, I said we will use the three basic equation: continuity, momentum, energy. So to find the velocity, you can use this momentum equation because you know P1, P2. Sorry, you know ρ1, ρ2, and V1 also. You can find V2. This is one equation. Otherwise, you can use energy equation also. H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. So what is H? It will be simply CPT1 plus V1 square by 2 is equal to CPT2 plus V2 square by 2. This equation also you can use it because we know T1, T2, V1, CP is constant, you can find the V2. Okay, this is how you have to find the velocity. Then you can find the Mach number. So in the AD2, whenever they asking the velocity, better you take first choice as energy equation. It is very simple because here it involves three variants: pressure, density, velocity, and all. But this involves only temperature and velocity. So always you try to choose this energy equation if you want to find velocity. Then second case. So the above one is the first case. We have taken both sides static properties. So P2 by P1, rho 2 by rho 1, we found it. The second case is static and stagnation. So in the static, simply I have taken MP rho T instead of 1, 2, 3, because here there is no 2. So simply I have taken P rho T. So this Mach number can be subsonic or supersonic. And assume, so we brought this flow to rest isentropically. There is no losses. Okay, we brought this flow to rest. That means Mach number is 0. Then at that point we are denoting pressure is P naught, density is rho naught, temperature is T naught. So this is the control volume. Then we are going to apply these two equations to this control volume. Okay, so same control volume. I'm just stopping the flow. Okay, so the Mach number is 0, so that I'm getting stagnation, pressure, temperature, density. Then if you apply this above two equation, we can derive the static and stagnation relation. See here in the station 2 it is P2, station 1 it is P1. Here in the station 2 it is P0, the station 1 it is P. That's what simply I converted here. Instead of P2 by P1 it is simply P0 by P. Instead of rho 2 by rho 1 it is simply rho naught by rho. Similarly, instead of T2 by T1 it is T naught by T. Okay, just direct conversion. It's very simple. Is that clear?
Yes, sir.
Okay.
Yes, sir.
Additionally, we are finding another one term, T naught by T in terms of Mach number. So once you know this inlet Mach number, we can find all this ratio P naught by P, rho naught by rho, T naught by T. Because once you know this T naught by T, we can substitute here and here, right? So that we can get all the parameters in terms of Mach number. So in the gas table, simply if you know the Mach number, by using the gas table, you can find all other properties. So these are all the direct conversion, and this alone we have to derive now. So T naught by T is equal to 1 plus gamma minus 1 by 2 m square. And just now I told, whenever if you want to relate temperature and velocity or Mach number, first option you have to go to the energy equation. So here also I'm going to take energy equation. And this is my control volume, static and stagnation. So apply to the first station. So it will be simply H plus V square by 2. And in the station 2, if you apply, so the velocity is 0. So this term get cancelled. And here I have H naught, because T naught, from that I can find H naught. Cp T naught is equal to H naught. Okay. So I have H naught. So this is your final energy equation for this control volume. Is that clear? So this is the general energy equation. Simply I apply to this control volume, so that it will be H plus V square by 2 is equal to H naught. Now from this I can derive that final term. So here, so we are finding T naught by T term. So it starts with the, so energy equation for this new control volume, H naught is equal to H plus V square by 2. Okay, it should be caps V, so no issues. And I don't want this H term, V term and all. I need only this temperature and Mach number term. So I have to convert everything. So first I'm converting this velocity into Mach number. So we know the relation V is equal to MA. And M we need it. We don't want this A. So that A term I'm writing into gamma RT. Okay, so I don't want this H, U, etc. So instead of velocity, I am taking the Mach number and speed of sound. And speed of sound term also I don't want. So I'm writing that into gamma RT. Then it is stopped. I cannot further modify this equation because I don't want this RT also. So to convert that, I'm including another one term, gamma minus 1 divided by gamma minus 1 in this term. Now what I can do, say I can take this gamma R divided by gamma minus 1, remaining same M square, same T, and this term gamma minus 1. Okay, same m square, same t. What is it? And this term just I'm keeping. Only this I'm rearranging. Gamma r divided by gamma minus 1. And you know what is gamma divided by gamma minus 1? That is Cp. So this is also same equation. Instead of gamma r divided by gamma minus 1, I'm substituting Cp. And we know what is Cpt. That is enthalpy H. Okay. So now I converted this u square into m square H gamma minus 1. Then substitute here. You will get H naught is equal to H plus, instead of u square, H into gamma minus 1 into m square and divided by 2. We can take H outside, so that you are getting, if you take H outside, you will get 1 plus gamma minus 1 by 2 m square. Again, I don't want this H term, this H naught H, that I can write it as Cp T naught is equal to Cpt into that remaining term. Cp get cancelled and rearrange this T, so that you will get the final form. T naught by T is equal to 1 plus gamma minus 1 by 2 m square. Okay. Then simply we have to substitute this T naught by T into the final P naught by P equation and rho naught by rho equation. So actually in the AD2, instead of fan, we will use reservoir storage tank. From that, the compressed air will be released through the nozzle, then test section. Okay. So we know the storage cylinder, the velocity or Mach number will be 0, and the pressure temperature are denoted by P naught and T naught. So here we have the stagnation property, and in the test section, we may achieve sonic, supersonic, subsonic, anywhere, anything. So here the properties are pressure and temperature. So to relate this stagnation and static, we can use that. This is one application. Okay. So this is the case 2, where we related static and stagnation. Now I am going to derive sonic and stagnation. You know, sonic means Mach number will be 1, and property we are denoting as P star, T star, rho star. This side stagnation only. So here the assumption is we are stopping the sonic flow. So here we stop this flow can be subsonic or supersonic. Okay, we are stopping the subsonic or supersonic flow, and we are making velocity is 0. And in the third case, we are stopping the sonic flow and making velocity is 0. So here also just direct conversion. So these equation simply you have to apply to this control volume. In the station 2, it is same only T naught, T naught, P naught, P naught. But in the station 1, instead of static, we have to mention sonic. Instead of P, it should be P star. That's what he converted here. Instead of T naught by T, here it is T naught by T star. And we know Mach number is 1. So instead of this Mach number, we substituted 1. Here also, it will be P naught by P star, T naught by T star. It should be T star, sorry. Rho naught by rho star, T naught by T star. Is that clear? And here, another one simplification we are doing. So this is the final equation. So we are substituting this gamma value, and instead of the equation, we are writing in numbers. That's what we are going to do in next slide. Okay. So this is the case 2 equation. Substitute, apply for the last control volume, sonic and stagnation. You will get this one. Okay. Then Mach number is 1. Remaining you can rearrange, simplify. You will get gamma plus 1 by 2. And mostly in the gas table, they used to mention T star by T naught, P star by P naught, like that. So they are taking inverse instead of T naught by T star. So they are taking T star by T naught. So this is the final form. Similarly, pressure also they are writing in the final form, because instead of T star by T naught, we know the value, substitute. Similarly, rho star by rho naught. We have 3 equations. So all 3 equations contains only gamma term. So this is compressible aerodynamics. We are dealing only with air. So we know gamma value of air. If you substitute, we can directly get the values. T star by T naught, P star by P naught, rho star by rho naught. So whenever you are relating sonic and stagnation, you no need to go for the equation. Directly you can take this value. For example, if you are using CD nozzle, again before that we have the reservoir. This itself I can explain. Okay. So previously I said we are measuring the pressure after the CD nozzle, right? For example, if you are measuring the pressure in the throat, you know, in the throat always it will be 1, where the properties are P star, T star. So we can relate stagnation and sonic using this relation. And here, instead of formula, directly we have the values.